Testing. Welcome, class. We're going to start section 4.6 today, and I'll be assigning that today, making it due a week from today. And you should see that pop up accordingly. I'd like to do one review problem here first. The review problem has to do with a confidence interval, which we covered back in section 4.5. This particular one, we have the Human Health Department for the state of Iowa has learned they can receive federal funding to start a program to reduce infestation of deer in the state if Iowa can show with 95% confidence that the percentage of deer carrying ticks infected with Lyme's disease was up to 40% or more. They decided to randomly capture a sample of 200 deer from across the entire state to test them for infestation and then release them. They found in that sample there were 89 deer infested. Find the 95% confidence interval to estimate the percentage of deer across the entire state that are infested. That's our first task here. Our confidence interval, you remember, had a formula, CI for confidence interval. It was going to be our sample proportion, p hat, plus or minus our z, alpha over 2, divided by 2 multiplied times the square root of n. P hat then is our sample proportion. In this case, it was 89 out of 200. So P hat, referred to as x over n. X is our number that were infested, and 200 was our sample size. Well, that turns out to be 0.445. That would be our sample proportion. Sometimes they call it our point estimate. It's another phrase that describes the value that comes out of the sample. Our z now is a little bit trickier. Alpha is the probability that we're going to be wrong, which if we're finding a 95% confidence, then alpha is that 5%. That 5% is split between the two tails on our normal distribution. So half of 5% is 0.025. The other half of the 5% is over there, which leaves 0.475 in these particular categories. I need the z-score that goes with 0.475 from the middle out. The 0.475 happens to be exact. That's describing from the middle out. The z-score is 1.96. That means this z-score was 1.96. This one is a negative 1.96. Those are the two z-scores that we're dealing with in this case. Those are the values that I'm going to be putting up in that numerator right there. 1.96, 2 multiplied times the square root of my sample size, which is 200. You would need to take the square root of 200, multiply it times 2, take that product, and divide it into 1.96. If you do so, you get the amount that we're going to add and subtract. That amount that we're adding and subtracting this time is 0.0693. This is referred to as our margin of error. This z over 2 times the square root of n is our margin of error. So if they had asked for what is the margin of error, we would give them that decimal right there. But now, because we wanted to find the confidence interval, I need to take this 0.445 and subtract this quantity, and then take 0.445 and add this quantity. So if I do that, I end up with the following values, I believe. 0.3757 all the way up to 0.5143. Let's make sure we understand what this means. This is a 95% confidence interval. That means that I am 95% sure that the percent of deer that are carrying the tick in Iowa is somewhere between 37% and 51%. The question that we have at the end here is, will the department be able to receive federal funding to implement a program to reduce that percentage? To get the federal funding, we had to show with 95% certainty that it was up to 40%. Unfortunately, this interval does not show that. Our sample was up to 40%. In fact, it was over 40. It was at 44.5. But because I ended up subtracting and adding, my interval goes below 40 down to 37% and up to 51. We are only 95% sure that the actual percentage of deer is somewhere between the 37 and 51. It could be 38 or 39. And because of that, I haven't shown with 95% certainty that it's 40% or more. It could be 38 or 39. So I would not be able to get the federal funding. Now, one of the things we could do, however, we kind of suspect that our percentage is above 40 because the one sample was well above 40, but this number took us back below 40. This number, our margin of error, 0.0693, in this case was too large. I can make that smaller by increasing the size of n. N was 200. If I bump it up to 400, that would make this denominator bigger, making the whole fraction smaller. So it would be a smaller number, maybe 0.03 or something like that. And in fact, when n is 400, this interval becomes 0.396, 0.494. Unfortunately, still not large enough because it went below 40. If I bump the sample size up to 500, then my interval becomes 0.4012, 0.4888. This time, it is entirely above 40. So I'm 95% sure that it's entirely above 40 if I could get a sample of 500 that would give me relatively the same point estimate or sample proportion. I would have to retry the entire experiment using 500. That is a challenge, capturing 500 deer across the entire state, but that's what it would take in this case. Recognize again, this is my point estimate, my sample proportion. This is my margin of error. I put them all together, I get my confidence interval. We would like to take a little algebra review here. Because we're going to be using an algebra review quite a bit in our lesson today. Our lesson today has to do with linear equations, of which this is an example. If I were asked to graph this equation, which graphs into a line, hence linear, a lot of ways I could do it. We started off, back when you were in Algebra 1, by making a chart. I would make up values for x. For example, I could let x be 2. If x is 2, I get 3 times 2 here, which would be 6. Bring the 6 over, I'd be left with 2y equal to 6. Y would have to be 3. If I want an easy one, I could let x be 0, because 3 times 0 would just drop out, meaning I could cover it up, and I would be left with 2y equal to 12. Y would be 6. I could also get another easy one by letting the y be 0. Then 2 times y would be 0. I could cover it up. It's gone. 3x would equal 12. X would have to be, in this case, 4. I have 4 points there, so I could graph this line. Two, 3 is right there. 0, 6 is up there, and 4, 0. These 3 should lie on a straight line. If they don't, I probably made an error someplace, and I should go back and recheck my points. So one way to graph that equation is to make a chart. One of the things that we really want to emphasize is that this chart could go on forever. In fact, there's infinite amount of ordered pairs that would work. I couldn't possibly list them all. But by graphing them, I'm basically graphing all of those points, an infinite amount of points. And I'm giving all the solutions at one time with one line, all the solutions to that equation. Now, another way we could have graphed that was to solve this for y. Here's why that's easier in many cases. I'm subtracting 3x from both sides. That would leave me 2y equal to a negative 3x and the 12. They can't be added together because one's an x and one is just a constant. I need to solve for y, so I would need to divide by 2. This is your algebra again. The 2's cancel, which is what I wanted. I want to get the y by itself. Gives me a negative 3/2. And 12 divided by 2 is 6. When it's solved for y, we say it's in slope-intercept form. The number in front of the x is our slope, which we usually call m. Sometimes they'll call it a. And the number by itself is our y-intercept, which we always call b. So you might see it as ax plus b or mx plus b. I think the most common is the mx plus b. Why does this make it easier for us to graph? Well, the answer is this. The y-intercept is where it crosses the y-axis. Notice it crosses at 1, 2, 3, 4, 5, 6. And our number here was 6. This number is my slope, which is how far I go up or down as I go to the right. So I'm going to go down 3 to the right 2. Notice down 3, I didn't quite have that exact. 1, 2, 3 down over 2. Should have been about right there. Down 3 more over 2. Down 3 more over 2. Down 3 more over 2. And I keep getting my line. By solving it for y, I can easily identify the slope. I can easily identify the y-intercept. Case in point, this one, there's no fractions, so it really means 4 over 1 times x minus 3. So I would find my y-intercept -3. My slope is positive, so I go up 4 to the right 1, up 1, 2, 3, 4 to the right 1, and there's my line using the slope-intercept form. One more example. This one, there's no number in front of the x, so it's really a 1x. That's really a 1 over 1. So I find my y-intercept, it's this 1 over here, but my slope is up 1 over 1. So I'm going to go up 1 over 1, and I have a diagonal line this time. Again, hopefully that looks familiar. Hopefully you recall doing that before. Another level is to find a line that goes through 2 points. Again, this is algebra background for our lesson today. Well, what I would like to do here, finding the line that goes through 2 points, I would love to go to that slope-intercept form. Unfortunately, I don't have the y-intercept in either of these points, and I don't have the slope. I need to find the slope from those 2 points. It has been a while, but your slope formula that you had back when you were a freshman in high school, slope between 2 points was to take the second y-coordinate minus the first y-coordinate over the second x-coordinate minus the first x-coordinate. So my second y is the 7. My first y is the 1. My second x is the 5, because these are, of course, x, y coordinates, right? And my first x is the -3. I have minus the first x, which is minus a -3. So I end up with 6 over 5 plus 3, which is 6/8, which reduces down to 3/4. So when I want to find the line through 2 points, like I have here, I've got to first find the slope using this formula. Maybe you remembered it by memory, but otherwise make sure you copy it down. My slope is 3/4, so I can put that in here. Now I just need to find the y-intercept. I can do that by recalling that if these 2 points are on the line, that means they must make the equation true. I want to say that again. If either point is on the line, it must make the equation of that line true. I'm going to put these points in for the x and the y. Because this one's a negative, I'm going to go with the one that has 2 positives. The x is going to be a 5, so that x has to be a 5 there. The y is a 7. This takes you back to algebra again. You have some fractions. This is going to be 15 over 4 plus b. I need to combine these 15/4 with the 7, so I need to change the 7 into fourths. I'm going to multiply the denominator 1 by 4, so I must take the numerator 7 times 4, which gives me 28/4. 28/4 would have reduced down to 7 over 1. Then I'm going to subtract 15/4 from both sides. And I get the b by itself. 28 minus 15 is 13/4. I found the b in my equation. I'm going to combine it now with the rest of it, the 3/4 x. So my equation will be y equals 3/4 x, that's from here, but instead of plus b, I'm going to write plus 13/4. Here's the equation of the line that goes through any 2 points. So I should be able to give you any 2 points and expect that you could do these two procedures to come up with that line. To that end, I would like you to try this one right here. I'm going to do it up here. I'm going to give you a head start. And hopefully you got, in this case, the y equal to a negative 3x plus 17. I chose the 0.52 to put in here. You may have chosen the 0.38. If you did, you would have put y equal to 8, x equal to 3, and you would have ended up getting the exact same equation. You can use either point. Either one would work. Well, the reason we're reviewing those Algebra 1 lines is because we're going to look at today what is frequently known as a form of linear regression. Linear regression, it's a pretty complicated sounding term in mathematics, but it basically boils down to taking lines and using lines to make predictions. That's what linear regressions are about. Now, getting the lines and using them is a little bit more challenging, but that's what our focus is going to be on today. The company's profit is a linear, that again is screaming at me right away, y equals mx plus b. It's a linear function. Produced by fixed overhead expenses and varying production expenses based on the number of items sold, combining to a varying income from sales based on a number sold. Records over the last 2 years have indicated that 2 years ago, when our sales were 3,000, our profit was 48,000. Last year, when our sales were increased, we went from 3,000 to 3,800. Our profit also increased to 56,000. We're told that it's linear. If this linear trend continues, as we push sales up, so if I can make it up to 4,300, what can I expect from my profit? Well, to get that expectation, I need to know what is the linear function. These really are two values that are related to each other. It's the sales related to the profit. It is like an ordered pair, 3,000 and 48,000. The second one is 3,800 and 56,000. We can think of these as ordered pairs. Then, to do this problem, it's no different than what you had earlier when I had two ordered pairs like this, and I had to find the line. Remember, we used the slope, and we plugged in a point. That's really what I got to do in the problem here. These are nice, easy ordered pairs. My ordered pairs are a little more complicated, but it's technically the exact same procedure. So I'm going to find my slope. It's the second y, 56,000, minus the first y, 48,000, divided by the second x, 3,800, minus the first x, 3,000. I end up here with, in this case, 8,000 divided by 800. Turns out to be a nice, easy number to work with, and I tried to make it that way, 10. So the m, my slope, is 10 in this problem. Now I can find the y-intercept b by putting in either the top point or the second point. I'm going to choose the top one. The y is 48,000. The x is 3,000. That gives me 48,000 equal to 30,000 plus b. If you subtract 30,000 from both sides, you get b to be 18,000. So here's my equation. I'm going to get the 10x from that equation, and I'm going to get the b from this one. So I have y equal to 10x plus 18,000. I can use that line now to predict whatever they're asking of me. It says if this linear trend continues, we push sales up to 4,300 units. Sales corresponded with these numbers, my x's. So we're asking, or basically saying, if this x over here is 4,300, what can I expect from my profit, which is the y? So I could put in 4,300. I get 10 times the 4,300 plus 18,000. That's going to be 43,000 plus 18,000. That's going to give me 61,000 when I'm done. I could expect my profit to be around 61,000 if we can push the sales up to 4,300. Basically, visually, what we did was this. We had one point, I'm just going to estimate it to be right there, and another point to be right there. We found the line. That was this line right here. And then we estimated what would happen at 4,300. Well, at 4,300, I'm going to get a point way up there. That's the 61,000. That's visually what was going on there. Records over the past number of years have indicated that our profits have indicated a linear trend. Same phrase. That means I can use that y equals mx plus b, relating the number of units sold with the profit. It's kind of like sales with the profit like we had last time. They have not been an exact linear function. That's why they said linear trend this time. It means all those points didn't make a perfect line. They've not been an exact linear function because sometimes we have different costs that come in for our raw materials. We have different variations on our sales, how much each item is worth. So I might end up with a graph, something like this. This graph gives me, on this axis, gives me the number sold. This axis gives me the profit in thousands. So apparently when I sold about, I would say 1.8 thousand I had around $3,000 profit. If I sold about 3,000 items, I had $4,000 or $5,000 profit. Notice that all these represent different ordered pairs. Unfortunately, they're not in a perfect line. So what we look for then is what we call our line of best fit. Now it's pretty obvious that this line over here is not a line of best fit. It's not even close to the data points. Our line of best fit would probably not be like that, probably not be like this. It would be kind of right in the middle, so to speak. I'm going to draw one line. I'm pretty certain it's not the exact line of best fit, but it might be something like that. If I could draw it again, looking at this point, I would probably make it just a little bit steeper. But here's a good estimate of the line of best fit. Going back to our problem, it asks what would be the best estimation of profits if we could hold the sales at 6,500. Well, 6,500 is right about here. So my profit, an estimate would be that mark on the line, which would be around 11,000. I could estimate the profit if I could bump the sales up to 8,000. This again is assuming this linear trend continues. So at 8,000, I would probably have something like $14,000 in profit. That's how we're using this line of best fit. To be a true line of best fit, here's what actually takes place mathematically. All of these errors, like the error from there to the point, the error from this point to the line, the error from this point to the line, the error from this point to the line, the error from this point, all of those errors need to be as small as possible. So for example, this line, these errors would have been huge amounts. Drawing the line or getting the best line would minimize all of these errors. That's what really is taking place mathematically to get this equation of a line. Well, to minimize all those errors, we are really looking at a line of best fit, which is an mx plus b. That's the same slope-intercept form that we worked with earlier. That proper m and proper y-intercept that would make all of those errors the smallest is what we call a line of best fit, denoted by, they typically go y hat equal to mx plus b. Y hat simply means we're using it as a line of best fit. Okay, now here's where your calculators come into play. You recall we had our Texas Instrument calculator. Your calculators will take ordered pairs like this one, these, and it will calculate your M and your y-intercept for you. It's kind of a complicated procedure, but it's not as complicated as doing it without your calculator. For example, I might have ordered pairs. I'm going to keep these really simple now. Let's go 4, 7. Let's go 5, 7. And let's go 8, 14. These 4 would likely not be on a straight line, but a line of best fit would be the best approximation of that line. I can get my slope using this formula. Don't copy it down. You really do not want to use this formula. I just wanted you to see it. XY means I would multiply each x times its corresponding y. So this would have been 6, 28, 35, and I believe 112. Then I would add them all up. So I would add 6 to 28 to 35 added to 112. And I would then subtract the sum of all the x's. Be 2 plus 4 plus 5 plus 8. Multiply that times the sum of the y's, 3 plus 7 plus 7 plus 14. Multiply it, subtract it from that, take it times how many ordered pairs. 1, 2, 3, 4 ordered pairs. That's just the numerator. Down here, I would have to square my x's and then add them up. So squaring the 2 would be 4. Squaring this one is 16. Squaring that one's 25, 64. I need to sum them up. So I would add 4 plus 16 plus 25 plus 64. Then I'm going to subtract, add up all the x's. So if I add up all the x's, 2 plus 4 plus 5 plus 8, subtract that, take it times how many, or excuse me, first square it, then take it times the number of ordered pairs, 1, 2, 3, 4. Wow, what a lot of work. We do not want to do that to get this M. We have a faster method. It's using our calculator, the TI-30X2S. It's not the only calculator that'll do that. Most of the calculators will do it in one form or another. I can't go over all the calculator possibilities. If you have one that is not this one, either go online, look for the manual, or have your manual yourself. But you will need to be able to do this on your calculator. So if you have the one recommended for this class, you can pause this video and get that calculator out. If you want to buy one, that's fine as well. But let's just say I've got these ordered pairs. I'm going to graph them right now, at least an approximation. 3, 5. Is right there. 2, 4. 4, 7. 3, 6. They don't make a perfect line. They're not bad, but our line of best fit should be somewhere kind of over them, making it as close as possible to that. That's what we're going to find once right now. So here's what we're going to do. We're first of all going to clear our data. This is very much like the standard deviation problem that we had a couple of chapters ago. So on my calculator, I punch second function stat. The calculator will show you at that point one variable, two variables. You're going to go right arrow until you hit clear data. It actually usually means you got to go right arrow twice. Once you get clear data, you hit enter. That took all the data out of your calculator from any previous problem. Then I start over, second function stat. I probably will need to go right arrow to get this two variable underline. The reason we want two variables, we have ordered pairs, two of them in every ordered pair. So when I get two variable underline, I hit enter. That just told my calculator I'm going to be putting ordered pairs in. So now I'm hit my data button, whatever way you want to pronounce it. The calculator will show you x sub 1. That's basically saying the calculator is asking for what's your first x. Your first x is 3, so you're going to plug 3 in. You're going to go down arrow once. The calculator will show you y sub 1. It's asking you what's your first y. Well, your first y is the 5. So you're going to punch the 5, go down arrow. It'll then say, what's your second x? You would go 2, down arrow, 4, down arrow, 4, down arrow, 7, down arrow, 3, down arrow, 6, down arrow. Don't forget to go down arrow on the last 6. When you've put all those in, you have all those ordered pairs in your calculator. Now we're simply going to go and find that y equals mx plus b. The calculator is going to give us the m. They actually call it an a in your calculator, and they're going to give you the y-intercept. The calculator has these ordered pairs in it. So I'm going to go stat variable. It's very much like we did earlier. The calculator will show you n, it'll show you x bar, it'll show you the standard deviation. You are actually going to go right arrow 12 times. When you go right arrow 12 times, you'll get to an A. that's your slope. That A becomes 1.5 from these ordered pairs. So when you see that A, you know you can put that in for your slope. Then you go right arrow once more and you get your B, which in this particular example is the 1. So here's your equation. It's your line of best fit or best fit line. The calculator gave me my slope and the y-intercept. You need to be able to do this very fast and almost in your sleep. So practice it a number of times if you haven't already mastered it. In a little bit, we're actually going to go one more concept. So after you have this B, which we found to be 1, if you go right arrow once more, you get R underlined. And it tells you the R is 0.9487. I'm going to go into what that R means in a few slides later. But right now, I just want you to remember how to get the R. You went 12 times to get the A, right arrow once more to get the B, right arrow once more to get the R. We'll talk about the R in just a moment. Once I have my line of best fit, I could now use it to predict, for example, if I wanted to predict one like 6 something, I could put the 6 in for the X. That would be 9 plus 1, it would give me a 10. I could also have given you the 10 and said, you find the 6. If I had given you the 10, you would put the Y to be 10, you'd subtract the 1, divide by 1.5, and you would get the 6 that way. So I could give you either coordinate, and you should be able to use this equation to find the other one. I would like you to try now putting these ordered pairs into your calculator, find A or M, the slope, find the y-intercept, and then just maybe write down the R as well. Don't forget to clear your data in your calculator before you try and add any more to it. You're looking at using those instructions to get that. If you haven't written those down or taken a picture of them, just pause and go back, rewind it till you get this slide clean before you had these on there. And see if you can get the 1.5 and the 1. But then do that with this one. I'm going to give you just a little bit of time to do that, and then I'll write the answers that you would have gotten. If you're not done, just go ahead and pause it. But what you should have gotten, this time the slope was not a nice number like 1.5, but rather it was a negative 0.6829. You might have rounded it off to 3. I'm just going to put the 29 on there. If you'd gone right arrow, you would have gotten your B value, would have turned out to be 6.2439. And again, you could round off to 2 decimal places if you wanted to. I'm going to use that as a line of best fit. We'll call it Y hat. But that would be finding the line of best fit for these ordered pairs. Now we're going to use that line to give the best estimate of the y coordinate that would go with x to be 3. In other words, they're asking, if x is 3, what is the y coordinate? I'm going to take the 3 and plug it back in. If I plug the 3 back in, it gets to be a little messy. I got to take this negative number times the 3 and then add it to the 6.2, etc. But what you'll end up with is the following number, I believe. When x is 3, I believe you get 4.1951. But I got to be honest, I'm having a hard time reading my writing there. Either it's 1951 or that's scratched out and it's just 951. I think it is 1951. Now they also want me to find the x coordinate that would go with 5.3. That would be if the y is 5.3, they want me to find the x coordinate. So I would take this 5.3, which is in the y position, I would put it in the y here, would take this number and bring it across, divide that by a negative 0.6829, and what I would get for that x number right there, x would have been 1.382. I guess I rounded that one off to 3. The y was 5.3. Being able to do all of these skills is going to be super important in this assignment as well as the test. Just a quick review. To get my line of best fit, I plugged all the ordered pairs into my calculator and had the calculator give me M and B. Calculator, again, you remember M they called A. So if you see an A there, it's referring to your slope. This one turned out to be a negative 0.6829. The B was this number. Then we use that equation to find either the y coordinate or the x coordinate if I'm given the other one. If I give you the x, you should be able to find the y. If I give you the y, you should be able to find the x. Okay? Again, you can practice this multiple times over, but your ability to use the calculator is crucial here on this kind of problem. I'm going to take it to another level now. Same concept, but just a little more challenging. The average hourly wage for a full-time employee in Iowa and the average tuition for only one semester at a 2-year junior state college is given in the chart on the next slide. Here we go. Find the line of best fit. That's at y equals mx plus b. I get my calculator to help me. We want to use it to estimate the tuition 2019 if the mean hourly wage had rose to $16 per hour. Well, here's the data. Okay. I need to think of these as if they're ordered pairs. In other words, this first one, think of it as an ordered pair of 11.82, where the y coordinate is 2,975. The second one, think of it as 12.28, the y coordinate 3,111. And I would do that for all of them. They're asking me to estimate what this would be. In other words, they're saying, if the x is 16, what is the y? I've got to use all of these ordered pairs to come up with the y equals mx plus b. As I mentioned, this one was a little more challenging just because these numbers are messier. They're not nice, easy coordinates like 2, 3 or something like that. These are messy numbers, but the principle that I'm doing is still the same. So I would have to clear my data in the calculator, punch in 2 variable, enter, hit my data button, and start off with 11.82, down arrow, 2,975, down arrow, 12.28, down arrow, 3,111, down arrow, 12.77 down arrow, 3,247 down arrow, all the way till I got over to here. I would not punch the 16 because I don't know that one yet. When I get all of those ordered pairs in, I would go stat variable, if you remember. After you punch the stat variable, you're going to go right arrow 12 times. And what you finally end up with is the following. You get your slope to be 394.877, I believe. Let me just double check that, yep. So that goes in for your M. Your y-intercept, the B, turns out to be a negative 1,774.66. There is your line of best fit. So if they asked you for the line of best fit, that's what you would do. You again could have rounded these off to 2 or 3, whichever one you're comfortable with. A messy problem. Have to be really diligent about not making mistakes as you plug these all in. In fact, it would probably be wise to do it twice over. Clear your data after the first time, run it through again, see if you get the same numbers. If you get the same numbers, it's a high probability you were likely to get that one correct. Okay? Then my x is a 16, so I would put 16 in for the x, multiply it times that, subtract this number, and I would get the y. I think it turns out that the y is going to be 4,543.37. And again, you could check that out at that point in time. Okay? Our last concept for today is our coefficient of linear correlation. That's that R that I talked about earlier that your calculator will also find. This R tells me how accurate my line is. Let me give you a visual of what I'm describing. If my ordered pairs were something like this, these are not real close to a line. I could still get a line of best fit. It might look something like that. But there's a lot of error here every time. This is not a super well-fitting line of best fit. If, on the other hand, my points look something like this, this time my line is closer to all the points. My line is a better predictor than what this one was. This one would not have been as good a predictor because the points are not very tight to the line. If my points had been something like this, almost exactly in a line, then my line would be a great predictor of other points. If my points look something like this, almost in a circle, I could still get a line from the calculator. It would just be a lousy predictor because there's just no pattern whatsoever. The closer the points are to being in a direct line, the closer R will be to 1. The further away they are from the line, the closer the R will get to be 0. So for example, if R would turn out, this one right here would probably be an R about 0.99, really close to 1. This one would also be pretty good. R would probably, I'm just guessing here, 0.95. This one would probably be something like maybe around 0.71 or something like that. This one would probably be an R around 0.07 or maybe something like that. I'm guessing on all of those. All of these R's would have been positive because my slopes were positive, they were going up. Had my slopes been negative, but really tight, really close to the line, then my R would have been really close to the negative one. But it would have been a negative. So if it's positive, it has a positive slope. If my R is negative, this one, for example, would have probably been a negative 0.98 or something like that. Bottom line is R is between the negative one and the positive one. If it's close to either of the ones, it means the line is pretty accurate. It's a good predictor. If the R is in the 90s, whether it's a negative 90 or a positive 90, it still means pretty good predictor. If the R is in the 70s, it's probably not as good a predictor. If the R is really close to 0, like it is here, it's a terrible predictor. The calculator will give you that value of R. Going back to this slide that we saw earlier, we used our line here to predict our y coordinate when the x was 16. And we found the y coordinate to be 4,543, etc. The question now is, how accurate was that? Well, I took a guess at what R was, but it turned out R was this value for that. R was equal to 0.979. Would everybody agree that that was very close to the 1? 0.979. That means that this prediction of 4,543.37 is got a lot of accuracy to it. We would be very confident in predicting that. Doesn't mean we're going to hit it exact, but we wouldn't be very far off. It would be a very good approximation of that because the R was so close to 1. If this R had been 0.8, we would have said it's a decent predictor. R to be 0.7 average, R to be 0.5, not a good predictor, R to be 0.3, very poor predictor. That again is how we use that value R. This is a type of problem that you can anticipate, as well as this kind of problem where I made the ordered pairs messy. But this problem with messy ordered pairs is really no different than this kind of problem with easy ordered pairs. But here's the concepts that you need to be able to do. You need to be able to take those ordered pairs, put them into your calculator, get a slope value, M or B, whatever your calculator, M or A, and then your y-intercept B to get your line of best fit. Then you would need to make a prediction. If I give you the X, in this case 11, you would have to predict, find the value of Y. Here I give you the Y to be a 13. You would have to find the value of X. That's using this line of best fit. And then you would find your R. That's known, that R, by the way, is called the coefficient of linear correlation. That's your R value. If the R is close to 1 or a negative 1, you would say my predictions are very reliable. If the R gets too close to 0 or a small variance from 0, you would say my predictions are not very reliable. To test this out for this one, here would be your answers that you can check on your own. When you plug these into your calculator, you're going to get the following line of best fit. Gotta follow that here a moment, I gotta get it. It is Y is equal to Sorry, it's taken me just a little bit of time here. Turns out to be a negative 0.069x plus 4.497. That's your line of best fit. Your R will turn out here to be a negative 0.115. Well, again, you should have something close to this from your calculator. This is your A value in your calculator, and this number should be your B value if you plugged in the ordered pairs correctly. Make sure when you plug in a -4 and the -1, you use the negative sign, not the subtraction sign. The negative sign there is down by the decimal point, okay? But again, make sure that you can get these numbers. These predictions, the 11, I might not have that. I apologize. I didn't have that one calculated out far enough. I did too. Turns out to be 3.734. And this one, the X turns out to be a negative 122.59 when the Y was at 13. Okay. This R value, would everybody agree it's not very close to a +1, it's not very close to a -1, it's actually closer to 0. So are my predictions reliable? No, because R is fairly close to 0. Again, anticipate being able to do all of these problems. Anticipate being asked all of these problems. You pretty much know what's coming. You just got to master it on your calculator. All right. If you didn't have this type of calculator, look for your instruction manual online, or look for a calculator like the one we had in class here and look to borrow that one. That is all that we have for today. So I'm assigning 4.6 here today, which I believe is a Tuesday, making it due next Tuesday from there. Have a good day for the rest of your day.